Hey everyone, welcome back to Chem Story. Today we're diving into an important topic in organic chemistry, alkene stability. Now you might be wondering, why does stability even matter? Well, when it comes to reactions involving alkenes, like additions or eliminations, the stability of the alkene can completely change the outcome. So if you understand which alkenes are more stable and why, you'll be in a much better position to predict reaction pathways. In this lesson, we're going to explore what makes one alkene more stable than another, and we'll break it down step by step. Let's get started. So first, how do we actually measure alkene stability? One simple and reliable method is by looking at the heat of hydrogenation. When an alkene reacts with hydrogen gas and becomes an alkane, it releases energy, and that energy change is called enthalpy, or delta H. Here's the key idea. The less energy it releases, the more stable the original alkene was. Let's look at three examples: 3-methyl-1-butene, 2-methyl-1-butene, and 2-methyl-2-butene. All three get hydrogenated to form the same product, isopentane, but the amount of heat released is different. 3-methyl-1-butene releases about 30.3 kilocalories per mole, 2-methyl-1-butene gives off around 28.5 kilocalories per mole, and 2-methyl-2-butene releases the least, only 26.9 kilocalories per mole. So what does that tell us? 2-methyl-2-butene is the most stable of the three, because it releases the least energy during hydrogenation. Alright, so what makes some alkenes more stable than others? A major factor is substitution. The more alkyl groups attached to the double bond, the more stable the alkene tends to be. Here's the general trend: unsubstituted, less than monosubstituted, less than disubstituted, less than tri-substituted, less than tetra-substituted. In short, more substitution, more stability. But it's not just about how many groups are attached. The way they're arranged also makes a difference. Take a look at these three: 1-butene, cis-2-butene, and trans-2-butene. If we compare their stabilities, trans-2-butene comes out on top. Why is that? We'll break it down in more detail in just a minute. For now, all you need to remember is this: transalkenes are generally more stable than cisalkenes. Now let's talk about the reason why more substituted alkenes are more stable, and that's something called hyperconjugation. It's a type of electron delocalization that helps stabilize the double bond, especially when there are more alkyl groups around it. We'll take a closer look at how it works in the next diagram. This diagram gives you a visual of what hyperconjugation actually looks like. Here, you can see a sigma bond, like a carbon-hydrogen bond, slightly overlapping with the antibonding pi star orbital of the double bond. That small overlap lets some of the electron density flow into the pi system, spreading it out just a bit, and that helps lower the overall energy of the molecule. You can think of it as a weaker version of resonance. It's not full delocalization, but it still creates a stabilizing interaction. So the more alkyl groups you have near the double bond, the more sigma bonds can participate. And that means more hyperconjugation and greater stability. Okay, now let's shift gears a bit and talk about bond strength and how orbital character plays a role in it. Here's the idea. The type of hybrid orbital involved in a bond can actually affect how strong that bond is. For example, an sp2 orbital has more s character than an sp3 orbital. And more s character means the electrons stay closer to the nucleus, so the bond ends up being shorter and stronger. And stronger bonds? They contribute to the overall stability of the molecule. Here we've got 1-butene and 2-butene, and next to each one you can see the types of orbital overlaps in their carbon chains. In 1-butene, we've got a mix of carbon-carbon bonds, 1sp3, sp3, 1sp3, sp2, and 1sp2, sp2 overlap. In 2-butene, it's a little different. You'll find 2sp3, sp2 overlaps, and 1sp2, sp2. Now, if we remove the carbon-carbon bonds that are the same in both molecules, we're left with one key difference. In 1-butene, what remains is an sp3 bond. In 2-butene, it's an sp2 sp3 bond. And since sp2 orbitals have more s character, That means the bond in 2-butene is shorter, stronger, and more stable. So overall, we can say that 2-butene is just a bit more stable. Now let's go back to what we mentioned earlier, the difference in stability between cis and trans alkenes. Just look at the 3D structures. In the cis isomer, both alkyl groups are on the same side, which creates steric hindrance because the bulky groups are too close. In the trans isomer, they're on opposite sides, so there's more space between them and less strain. That extra space makes trans more stable than cis. It's a small difference in structure, but it clearly shows how 3D geometry can affect stability. To back this up with data, let's take a look at the hydrogenation values for cis and trans isomers. The cis isomer releases about 120 kilojoules per mole, while the trans isomer gives off slightly less, around 116 kilojoules per mole. And remember, the less heat released, the more stable the alkene was to begin with. So overall, the trans isomer comes out more stable. So now let's talk about cycloalkenes. These are alkenes where the double bond is part of a ring. Just like cycloalkanes, their stability depends a lot on ring size, mostly because of ring strain, including angle strain, torsional strain, and steric hindrance. Let's start small. Cyclopropene and cyclobutene have tiny rings, so their bond angles are way off from ideal, and that puts a lot of strain on the structure. They're real molecules. We can make and isolate them, but energetically, they're not very stable. Things get better with cyclopentene. This 5-membered ring can hold a double bond without too much trouble, but only in the cis form. As the ring gets bigger, strain decreases, and the double bond fits in more easily. Alright, now let's take a look at how acyclic and cyclic alkenes differ in stability. In open chain systems, trans isomers are almost always more stable than cis isomers. Why? Because there's less steric hindrance, the bulky groups are farther apart. That same idea, repulsion between substituents, also applies to cyclic alkenes, but things get a bit more complicated because of the ring geometry. So let's take a closer look at how that plays out in rings. When it comes to cycloalkenes, whether the double bond takes the cis or trans form depends on whether the ring is big enough to handle it. Cis isomers don't need much space. Even a 5-membered ring, like cyclopentene, can hold a cis double bond without too much strain. But trans isomers need much more room. In smaller rings, forcing a trans configuration causes too much angle and torsional strain. That's why trans cycloalkenes don't really exist, unless the ring has at least 8 carbons. So here's the general rule. Cis forms are fine starting at 5-membered rings, but trans forms only become stable in rings with 8 or more carbons. Before we wrap up our discussion on alkene stability, there's one last concept we need to cover, and that's Brett's rule. This rule applies to bridged bicyclic compounds, rigid structures where 2 rings share a bridgehead carbon. So what does the rule say? You can't place a double bond at a bridgehead carbon unless the ring system is large enough, meaning at least one of the rings has 8 or more carbons. Smaller rings just can't achieve the flat geometry needed for a double bond. Forcing it causes too much strain, and the molecule becomes unstable or won't form at all. So Brett's rule isn't just a rare exception. It's a real geometric limitation based on how much strain the ring can handle. Let's make this even clearer with a few examples. On the left, you can see a typical bridged bicyclic compound. The bridgehead carbon is marked, and that's what we're focusing on. In the middle example, someone tried to place a double bond at that bridgehead, but the rings are just too small. The geometry doesn't work, and the strain is way too high. That kind of structure simply can't exist. But on the right, we've got a larger ring system, and now the bridgehead carbon can support a double bond. There's enough room for the p orbitals to line up properly so the pi bond can form without distorting the structure. Just keep this in mind, double bonds at bridgeheads only work when the rings are big enough. Otherwise, you're violating Brett's rule, and the molecule just won't hold up. That wraps it up for today. Thanks so much for watching, and I'll catch you in the next Chem Story video.